Hello my friends and welcome back to the You Can Do TV channel. The plate rolling process for wind energy components using an MCB 4-roll system is designed for precision, structural integrity, and efficiency in handling large-scale steel sections. Operations begin with cutting and beveling, where steel plates are trimmed to exact dimensions and edges are beveled to facilitate strong weld joints. The rolling stage follows, with the 4-roll configuration ensuring accurate curvature and minimal material handling, producing perfectly cylindrical or conical sections. Next comes welding, performed in multiple orientations, circular, vertical, and horizontal welds, to join rolled sections into complete cylindrical structures. Each weld undergoes rigorous inspection using non-destructive testing methods to ensure compliance with strict industry standards. The process then advances to assembly works, where internal supports, flanges, and mounting interfaces are installed. For offshore or large wind tower segments, dry dock assembly is carried out, preparing units for transport. Load-out preparations involve securing components, verifying weight distribution, and ensuring safe handling during transit. Finally, the completed sections are loaded out and delivered to installation sites, ready to be integrated into wind turbine systems. This method ensures optimal strength, precision, and durability for wind energy infrastructure. Road infrastructure has long served as a critical component in connecting populations, enabling economic exchange, and supporting the development of civilizations. The transition from rudimentary caravan trails to engineered roadways accelerated significantly in the early 20th century with the adoption of hot-mix asphalt, which provided a durable, high-performance surface capable of accommodating modern vehicular traffic. Today, this material is the standard for the top layers of highways, bridges, and airport runways. The Sigma Compact series utilizes a containerized modular design, ensuring structural rigidity, safe overseas transport, and rapid assembly. With capacities of 120 to 200 ton per hour, it combines high-efficiency burners, automated control systems, and optimized material flow paths to maintain consistent asphalt quality. For high-volume applications, the Sigma Prima series incorporates robust structural frames, high-capacity drying drums, multi-stage dust collection, and high-performance mixers. Its modular design allows production rates from 200 to 340 tons per hour while maintaining tight tolerances in mix composition. The Sigma Mobile series is built on 4 fully pre-wired trailers, integrating heating, mixing, and control units for field deployment. Operating at 100 to 160 ton per hour, it ensures fast setup, high mobility, and precise production control. Across all models, Sigma's engineering emphasizes durability, automation, and compliance with strict asphalt quality specifications. The construction of a 4 megawatts power generator begins with the precision engineering of its core component, a high-performance General Electric GE engine, specifically adapted for continuous heavy-duty operation. The process starts with the fabrication of the generator frame and base, using heavy-gauge steel structures designed to withstand dynamic loads and vibration over decades of service. The GE engine block, machined from high-strength alloy steel, is carefully assembled with forged crankshafts, precision-balanced rotors, and reinforced cylinder heads to ensure optimal combustion efficiency. Each major assembly undergoes dimensional checks and non-destructive testing to verify integrity before integration. The alternator section is built around a laminated steel stator core, wound with high-conductivity copper windings insulated for high-voltage performance. The rotor, precision balanced to micron tolerances, is coupled directly to the GE engine's output shaft, enabling efficient conversion of mechanical energy into electrical output. Bearings, cooling systems, and lubrication circuits are installed to support continuous operation under high thermal and mechanical stress. Control and monitoring systems, including automatic voltage regulators, protective relays, and digital control panels, are wired into the unit to allow precise output management and fault detection. Once assembled, the generator is connected to a fuel system, exhaust treatment unit, and sound attenuating enclosure. Final commissioning involves a series of load bank tests, running the generator at various loads up to its 4 megawatts capacity. Parameters such as voltage stability, frequency control, thermal performance, and vibration levels are recorded and fine-tuned. Upon passing all acceptance criteria, the generator is prepared for transport, ready to provide reliable large-scale power for industrial facilities, emergency backup, or grid support operations. The Drum Twister Machine 3200 is engineered for high-efficiency twisting of fibers, wires, or textile strands, delivering consistent and precise results across industrial-scale operations. The machine utilizes a robust drum mechanism that rotates at controlled speeds, allowing strands to be evenly twisted with minimal variation. Adjustable tension controls ensure uniformity while preventing material stress or breakage. The 3200 features an automated feeding system, guiding fibers smoothly onto the drum for continuous operation, reducing manual intervention, and optimizing throughput. Safety mechanisms and emergency stops are integrated to protect operators and maintain stable performance during high-speed twisting. The machine also supports varying twist ratios, making it versatile for different material specifications and applications. Its heavy-duty frame and precision-engineered components ensure long-term durability and minimal maintenance. Ideal for textile, cable, and rope manufacturing, the Drum Twister 3200 combines reliability, precision, and efficiency in one industrial-grade solution. In 2019, UOS achieved a feat that pushed the boundaries of industrial manufacturing, setting a new world record in grommet production with a staggering 420 mm diameter. This colossal component, boasting a circumference of approximately 94 meters and an impressive single-piece weight of 60 metric tons, stands as a testament to engineering mastery and precision craftsmanship. At the heart of this achievement was the CGBL 15306, itself holding a world record with a mass of 15,306 metric tons, delivering the power and stability needed for such monumental fabrication. Every stage of production demanded exacting attention to tolerances, material integrity, and dimensional accuracy. The sheer scale of the grommet meant that conventional methods were redefined, with custom handling, shaping, and inspection processes developed specifically for the task. This record-breaking accomplishment is more than just numbers. It's a demonstration of how vision, technology, and expertise converge to redefine what's possible in heavy industry. With UOS's success, the benchmark for grommet manufacturing has been set higher than ever before, inspiring the next generation of engineering achievements. The motor winding process for a WEG 250 kilowatts, 340 HP, 1000 U per minute electric motor is a precise and methodical operation, essential for ensuring optimal motor performance and efficiency. The focus is on winding high-purity copper wire into the stator core. First, the stator slots are carefully insulated to prevent short circuits and improve thermal resistance. Pre-measured lengths of copper wire are then guided into the slots using specialized winding equipment, ensuring uniform coil tension and alignment. Layer by layer, the windings are arranged to achieve the required number of turns, optimizing electromagnetic field generation. After winding, the coil ends are secured, and connections are soldered or crimped according to the design specifications. The stator is then impregnated with insulating varnish, baked to enhance dielectric strength, and prepared for final assembly. This meticulous process guarantees reliable power delivery and long service life for the high-performance motor. At the Griffin Pipe Products Lynchburg facility, the production of ductile iron pipe is executed through a fully integrated, carefully monitored process that begins with the reception of raw materials and ends with the delivery of precision-engineered finished products. Raw material supply includes iron scrap, steel scrap, pig iron, and selected ferroalloys, each delivered by rail or truck. These charges are loaded into large-capacity, medium-frequency electric induction furnaces, where melting occurs under continuous temperature monitoring. The molten bath is analyzed spectrographically at regular intervals, allowing precise adjustments of carbon, silicon, and other alloying elements. Slag removal is performed to maintain metal cleanliness and prevent inclusions in the casting. Once the base iron reaches the required composition, it is transferred into treatment ladles for the critical spheroidization stage. In this step, magnesium ferrosilicon alloy is placed in the bottom of the ladle, and as the molten iron is poured in, an exothermic reaction occurs, transforming flake graphite into spheroidal graphite. This structural change is what imparts ductility and toughness to the final product. The reaction is tightly controlled with respect to temperature, alloy quantity, and time, and all parameters are recorded for quality assurance. Immediately following treatment, the molten metal is poured into centrifugal casting machines. Each pipe mold consists of a water-cooled, precision-machined metal cylinder that spins at high speed, causing the molten iron to spread evenly along the mold wall through centrifugal force. Cooling is immediate and uniform, producing a dense, fine-grained microstructure. Operators adjust rotational speed and cooling water flow to achieve the specified wall thickness and metallurgical properties. Freshly cast pipes proceed to an annealing furnace, where they are reheated to controlled temperatures and held for specific periods to relieve internal stresses, refine the graphite structure, and achieve the target mechanical strength and elongation. Controlled cooling follows, preventing distortion and ensuring dimensional stability. Every annealing cycle is documented, and furnace atmosphere and temperature are monitored by calibrated sensors to ensure repeatability. After annealing, pipe exteriors and interiors are cleaned in an automated shot blasting system, which uses high-velocity steel shot to remove oxidation, casting scale, and residual sand. This prepares the surfaces for machining and coating. Precision machining operations are carried out in a dedicated machine shop equipped with CNC lathes, conventional lathes, facing machines, and groove-cutting tools. Joint ends are formed according to customer requirements, including tightened push-on joints, mechanical joints, or flanged ends. Machining tolerances are verified using calibrated gauges and micrometers, ensuring proper fit during pipeline assembly. Dimensional accuracy is critical, as even minor deviations can affect sealing performance in the field. For water service applications, an internal cement mortar lining is applied to inhibit corrosion and improve hydraulic flow. This is performed using centrifugal lining machines, which evenly distribute cement slurry across the pipe interior while the pipe spins at controlled speed. The spinning compacts the mortar and ensures a smooth, uniform surface. The lined pipe is then cured in a controlled environment, with humidity and temperature maintained to prevent cracking and ensure bond strength. External protective coatings follow, typically consisting of an asphaltic paint or other corrosion-resistant systems applied either by spraying or dipping to a uniform thickness. Coatings are inspected for coverage, adhesion, and thickness before curing or drying. Hydrostatic testing is conducted on every pipe to verify its structural integrity and leak tightness. Pipes are filled with water and pressurized to levels above their intended service pressure, held for a specified duration, while inspectors monitor for leaks, bulges, or deformation. Test data is recorded and tied to each pipe's identification number for traceability. Following testing, a final inspection is carried out to confirm all dimensional specifications, surface finish quality, coating integrity, and lining condition. Any non-conforming pipes are either reprocessed or rejected. Approved pipes are marked with essential identification information, including size, pressure class, material specification, manufacturing date, and heat number. This ensures complete traceability from raw material batch to final installation. The marking is applied in durable paint or stamped for long-term legibility. Finished pipes are bundled or stacked with protective spacers to prevent damage to linings and coatings during handling and transport. Loading onto trucks or rail cars is done using slings or padded hooks to avoid surface damage, with all loads secured according to transportation safety standards. Supporting this manufacturing operation is an on-site quality control laboratory equipped with advanced analytical instruments, including optical emission spectrometers for chemical analysis, tensile testing machines for mechanical property verification, Brunel and Rockwell hardness testers, and metallographic microscopes for microstructure evaluation. Laboratory technicians work in close coordination with production supervisors to address any deviations promptly. Every stage of the process, from raw material intake to final shipment, is documented under a comprehensive quality management system in accordance with ISO 9001 principles. This rigorous process control ensures that ductile iron pipes manufactured at the Lynchburg facility consistently meet demanding mechanical, dimensional, and corrosion resistance requirements. The manufacturing of high-performance ductile iron rolling mill rolls follows a tightly controlled sequence to guarantee dimensional accuracy, mechanical strength, and operational reliability. The process begins with melting in medium-frequency induction furnaces of varying capacities: 500 kilograms, 750 kilograms, 3 tons, and 5 tons, depending on batch size. Charged materials are carefully proportioned to achieve the target alloy composition. During melting, temperature is monitored with thermocouples, and chemical composition is verified using a spectrographic analyzer. Once the molten metal meets specification, it is poured into precision-prepared sand molds with a molding capacity of 40 kilograms every 15 seconds. Spent sand is processed through a reclamation system to maintain consistency and reduce waste. After solidification, castings undergo surface cleaning in a 1.5-ton shot blasting unit to remove residual sand and oxides. Heat treatment follows in a 20-ton capacity furnace, applying controlled heating, soaking, and cooling cycles tailored to the specific grade, ensuring optimal microstructure, tensile strength, and wear resistance. For rolls in roughing, intermediate, and finishing positions, metallurgical properties are matched to operational loads and thermal conditions. Once heat treatment is complete, the rolls move to the machining stage, where a combination of conventional and CNC equipment, including lathes, vertical and universal milling machines, a CNC double-column machining center, radial drills, a vertical lathe, a vertical bandsaw, and a 150-ton press, ensures precise shaping and finishing. Dimensional tolerances, concentricity, and surface finish are measured at multiple stages, while hardness testing confirms compliance with specification. Throughout production, quality control is applied at every step, from raw material input to final machining, ensuring defects are identified and corrected early. Finished rolls are packaged securely after final inspection to protect surfaces and maintain geometry during transportation. The entire workflow is executed under strict process discipline, with traceable documentation and compliance to recognized industrial standards, ensuring each component is ready for demanding service in the steel rolling industry. Amid the rhythmic hum of heavy industry, the CDRA 500Z stands as a testament to precision under extreme force. Built for the rigorous demands of railway engineering, this hydraulic press transforms the complex task of wheel set adjustment into a finely tuned process of controlled power. In a single, seamless operation, it aligns, presses, and verifies each component with unwavering accuracy. Built for cold pressing operations, this advanced machine eliminates the need for guide bushings, while enabling accurate axle turning, making it a highly versatile tool for both manufacturing and maintenance. At its core, the CDRA 500 operates as a horizontal press with a robust columnar construction. The press cylinder, mounted in the stationary crossbeam, delivers immense hydraulic force directly onto the wheelset components, working against the bearing crossbeam. The moving crossbeam travels along precision-threaded anchors with preset measurement positions, ensuring repeatable accuracy for every pressing cycle. This press is capable of pressing on wheels, pressing off worn components, and even pressing parts between wheels, making it an all-in-one solution for railway workshops. The supporting crossbeam features hydraulic wheel centering, ensuring perfect alignment during assembly. Meanwhile, the rear crossbeam is equipped with hydraulic axle centering, guaranteeing that every press operation maintains precise geometry. A sophisticated control system manages all press functions, from force application to real-time diagnostics. Operators can monitor pressing forces, positioning, and fitting parameters, while the system automatically identifies errors to prevent damage or misalignment. Designed with both power and precision in mind, the CDRA 500 Zetas stands as a vital asset for modern rail transport maintenance and production facilities, delivering flawless wheelset adjustments with efficiency, safety, and uncompromising accuracy. In the world of high-performance engineering, few components demand such uncompromising precision as the big-diameter seamless cold-drawn stainless steel tube. Designed for critical applications in energy, petrochemicals, marine engineering, and heavy industry, these tubes must combine exceptional mechanical strength with absolute dimensional accuracy. Achieving this level of performance requires a process that harnesses both immense power and meticulous control, driven by a hydraulic cold drawing machine with an over 650-ton power capacity. The journey begins with the production of a seamless hollow billet, typically formed through hot piercing and rolling. Once cooled, the billet undergoes surface cleaning to remove oxide scale and contaminants, ensuring a flawless starting point. A specialized drawing lubricant is then applied, reducing friction and preventing damage during the drawing operation. In cold drawing, the billet is gripped and pulled through a precision-engineered die while supported internally by a mandrel. This high-force operation reduces the tube's diameter, refines wall thickness, and improves its internal surface quality. The process induces work hardening, significantly increasing tensile strength while maintaining excellent corrosion resistance, a hallmark of stainless steel. Multiple passes through progressively smaller dies, interspersed with intermediate annealing, allow for controlled shaping without compromising ductility. Dimensional tolerances are measured to within fractions of a millimeter, and every tube undergoes rigorous, non-destructive testing to verify structural integrity. The result is a large-diameter, seamless stainless steel tube that delivers unmatched reliability in the harshest environments. Capable of withstanding extreme pressure, temperature fluctuations, and corrosive media, these tubes represent the perfect union of raw power and refined precision, a testament to advanced metallurgical engineering and the relentless pursuit of quality. In precision gear manufacturing, where both speed and accuracy are critical, the Gleason 1500G Titan Power Grind delivers a complete, high-performance solution. Designed for modules up to 14 with a large number of teeth and expandable for modules up to 44, it combines threaded wheel grinding for productivity and profile grinding for precision in a single automated system. The cycle begins with the loading of the threaded grinding wheel. Gleason's patented dressing concept eliminates the need for setup before dressing, reducing preparation time and ensuring precise geometry. Dressing is performed sequentially on the left flank and the right flank, creating the exact profile required for high-speed roughing. The system's automatic coolant nozzle adjustment then positions flow accurately for threaded wheel grinding, maintaining stable temperatures and clearing chips during operation. In the roughing stage, a coarse grit threaded wheel is used for maximum material removal rates. For example, with module 1484 teeth, face width 255 mm, helix angle 11 degrees, the Titan Power Grind achieves up to 36% faster cycle times compared to conventional profile grinding without compromising accuracy. The machine then transitions seamlessly with its fully automatic tool change system. In less than 1 minute, it switches from threaded wheel grinding (TWG) to profile grinding (PG), with up to 4 tool stations available. This design eliminates interference risks between the workpiece and grinding tools, ensuring smooth, uninterrupted production. Next, the profile grinding wheel is loaded. Again, coolant nozzles automatically reposition to match the new tool. Dressing is completed for both flanks, preparing the wheel for high-precision finishing. In this stage, wheel grit size is carefully selected according to the desired surface finish, enabling the production of gears that meet the strictest quality requirements. When producing large module gears up to 44, the power grind function comes into play. The roughing grinding wheel is dressed, then a coarse grit profile wheel is used for aggressive stock removal. Automatic coolant control keeps the process thermally stable. For a case such as module 25, 18 teeth, face width 495 mm, helix angle 19.6 degrees, the system delivers 30% faster grinding times and surface finishes as fine as raw less than 0.2 micrometers. Roughing in these heavy-duty cases uses a specialized coarse grit wheel for higher removal rates and reduced cycle times. Once the bulk of the material is removed, the Titan Power Grind initiates another fully automatic tool change in under 1 minute, loading a finishing wheel with fine grit size. This wheel is dressed to precise specifications, then used for the final profile grinding pass. The result is flawless tooth geometry, superior surface finish, and excellent long-term gear performance. The integrated design of the Gleason 1500G Titan Power Grind offers a balanced combination of productivity and precision. Threaded wheel grinding accelerates the roughing process, while profile grinding guarantees dimensional accuracy and surface quality. From wheel loading to final gear inspection, every stage is engineered for efficiency, repeatability, and world-class performance. Supporting features like automatic dressing, intelligent coolant nozzle positioning, and multi-station rapid tool change maximize uptime and flexibility. Whether manufacturing high tooth count module 14 gears or large, heavy-duty module 44 components, the Titan Power Grind consistently delivers industry-leading results. This is more than just a grinding machine. It's an automated, intelligent gear finishing platform designed to push production speed while protecting precision at every step. In the world of heavy machining, the SCOD HCW2200 stands as a true giant, a horizontal boring and milling machine built to handle the largest and toughest components with absolute precision. During power testing, the machine is pushed to its operational limits. The massive spindle drive engages, delivering immense torque to simulate real-world cutting forces. Under maximum load, every structural element from the robust column to the precision ground table is evaluated for rigidity and stability. Cutting trials begin, with varied feed rates and depths of cut, challenging the machine's ability to maintain accuracy while removing large volumes of material. Advanced sensors track spindle speed stability, torque consistency, and positional accuracy across all axes. Throughout the process, the HCW2200 demonstrates unwavering control, supported by a sophisticated CNC system that ensures performance under the harshest conditions. Passing these tests confirms its readiness for industries where precision is non-negotiable, from energy production to shipbuilding, and where only machines of this caliber can deliver. Hey. Step into the world of real-time 5-axis machining, where precision meets power. At the heart of this process is the 5AX100 machine vise, gripping workpieces at any height with an impressive 42 kilonewtons clamping force. This ensures the 100 kilowatt spindle can push through even the most demanding materials without compromise. Watch as the machine glides seamlessly across multiple axes, sculpting complex geometries in a single, uninterrupted setup. Sensors embedded throughout the system track every motion, instantly adjusting to maintain micrometer-level accuracy. The need for repeated repositioning eliminated. Cycle times shrink, while surface finishes remain flawless. Sophisticated cooling and lubrication systems work in perfect harmony with the toolpaths, preventing overheating and material distortion. Advanced CAM programming orchestrates intricate movements, interpolating all 5 axes simultaneously, while the sturdy frame and dynamic drives suppress vibrations to deliver pristine results. From aerospace components to automotive molds, every piece benefits from unmatched efficiency, adaptability, and precision. This is not just machining, it's a symphony of engineering excellence, where every movement is calculated, every cut optimized, and every surface finished to perfection. Experience the future of manufacturing, where power and precision converge in perfect harmony. Forging steel balls using a pneumatic hammer involves a process where precision, efficiency, and mechanical force are combined to produce high-strength components for mining, milling, and grinding applications. Unlike steam hammers or air hammers that rely on an external compressor, the pneumatic forging hammer is equipped with a self-contained cylinder, eliminating the need for supplementary power plants. This design improves energy efficiency and reduces setup complexity. The operator controls the hammer through a hand lever or foot pedal, allowing smooth transitions between various modes: idle run, top setting, pressing down, single blow, and either light or full series blows, depending on the forging requirements. During production, heated steel billets are placed under the hammer's die, where controlled blows shape them into spherical forms. The forging process refines the grain structure of the steel, enhancing hardness, wear resistance, and impact strength. After forging, the balls are trimmed, normalized, and heat-treated to achieve consistent metallurgical properties. Pneumatic hammers offer excellent repeatability and control, making them ideal for producing uniform steel balls in large quantities while maintaining dimensional accuracy. This combination of power, precision, and operational simplicity ensures high productivity and consistent product quality in industrial forging operations. It all starts with high-grade alloy steel, chosen for its strength and durability. Forged into shape, each ring and rolling element enters the heat treatment stage, where controlled temperatures transform the metal's structure for maximum hardness and fatigue resistance. Precision CNC machining follows, shaving tolerances down to microns. Fine grinding polishes the raceways to perfection, creating surfaces so smooth they can handle millions of rotations without fail. Assembly is meticulous, rolling elements matched perfectly with cages and raceways for flawless load distribution. Every bearing then faces intense quality checks, from vibration analysis to endurance testing. The result? A component ready to deliver reliability, efficiency, and performance day after day, revolution after revolution. In every machine that moves with precision, there's a silent hero: bearings. They carry the load, reduce friction, and keep motion smooth. Whether it's a car thundering down the street, a turbine spinning at full speed, or a conveyor running non-stop in a factory. Landers Universal's pressure cooker production is a precisely engineered process, focused on durability, safety, and performance. Since 1954, the company has specialized in manufacturing aluminum-bodied cookers, chosen for their optimal heat conduction and corrosion resistance. The vessels are produced through controlled forming and machining operations to achieve uniform wall thickness and perfect circular geometry, ensuring even pressure distribution during cooking. A key technical feature is the external locking system, designed to withstand internal pressures safely while allowing quick, secure lid engagement. The sealing ring, gasket, plays a critical role in maintaining the cooker's airtight environment. To prevent premature wear, it must be removed for cleaning, avoiding unnecessary stretching or abrasion. Any degradation of the gasket can compromise sealing efficiency, leading to steam leaks and reduced cooking performance. The pressure control system relies on precision-drilled vent holes, which must remain unobstructed to regulate internal pressure accurately. After each use, these vents should be cleaned to prevent blockages that could cause unsafe pressure levels. Filling guidelines are equally important. Maximum safe volume is 3/4 of the vessel's capacity, identified by the rivets on the handle. This ensures adequate steam space for controlled pressure buildup. Every design parameter, from the alloy composition to the safety valve calibration, is based on decades of field data and continuous refinement. The result is a cooking vessel engineered for long service life, with over 18 million units in operation worldwide, many still in use after decades of daily cooking. Yakan. The manufacturing of the cylindrical body of a 120-liter steamer in Mexico using traditional manual lathe metal spinning is a process that combines craftsmanship with precise metal forming techniques. The operation begins with the selection of a circular aluminum sheet, cut to the required diameter and thickness. Aluminum is chosen for its excellent heat conductivity, corrosion resistance, and ductility, which allows it to be formed without cracking. The blank is cut with a guillotine shear or CNC cutter to achieve perfect roundness, as even minor deviations can cause vibration or imbalance during spinning. Once the blank is prepared, it is carefully centered and mounted against a pre-shaped steel mandrel. The mandrel's profile exactly matches the internal contour of the finished steamer body. This mandrel is fixed to the spindle of a large, manually operated spinning lathe. The aluminum blank is pressed tightly against the mandrel using the tailstock and a live center, ensuring concentricity and secure holding. The lathe is started at a moderate rotational speed. The artisan, standing in front of the spinning workpiece, uses a long-handled, hardened steel spinning tool, roller or spoon, supported on a tool rest. By pressing the roller against the rotating aluminum, the operator gradually forces the metal to conform to the mandrel's shape. The forming is done progressively in several passes. The first pass applies light pressure to initiate stretching, followed by deeper forming passes that gradually push the metal down the mandrel toward the base profile. During this process, lubrication such as wax or oil may be applied to the contact area to reduce friction, improve surface finish, and prevent tearing of the aluminum. The operator must constantly control the tool's angle, pressure, and feed rate to ensure uniform wall thickness and avoid over-thinning in any section. Unlike automated systems, manual spinning relies heavily on the craftsman's skill, as adjustments are made in real time based on the sound, vibration, and feel of the material under the tool. Once the cylindrical wall is nearly formed, the operator makes finishing passes to refine the contour and smooth the surface. These passes not only improve aesthetics, but also strengthen the metal through work hardening, enhancing durability for heavy cooking use. Any excess material at the rim is trimmed using a cutting tool mounted on the lathe, producing a clean, precise edge. This edge will later be prepared for joining to the base and for fitting any reinforcing rings. At the end of spinning, the steamer body is stopped, the tailstock is retracted, and the formed cylinder is carefully removed from the mandrel. The part is then checked for roundness, wall thickness uniformity, and surface quality. Any sharp edges are lightly deburred, and the body is stacked for subsequent manufacturing steps, such as welding the base, attaching handles, and fitting the lid. This manual metal spinning method, while slower than automated production, offers excellent control over forming quality, produces seamless cylindrical bodies with high structural integrity, and preserves the artisanal manufacturing tradition that remains valued in specialized cookware production. Traditional aluminum pot making is a craft-based metalworking process that combines manual skill with basic forming tools. It begins with aluminum discs, which are heated to improve malleability. Using a manual or motorized spinning lathe, the craftsman shapes the disc over a steel mold, gradually pressing and smoothing it into the desired pot form. Once the basic shape is achieved, the pot is trimmed and finished, removing excess material and refining edges. Handles are often riveted or welded on, and the surface may be polished or anodized for protection. This method allows for thick, durable walls and a consistent, rounded geometry. Despite advances in industrial manufacturing, traditional spinning remains valued for producing strong, long-lasting cookware with a handcrafted quality. Witness the precision and power of the Abbend BMBB25 flanging machine, a specialized solution for forming perfect flanges on large metal components. Engineered for heavy-duty industrial applications, this machine handles thick plate materials with ease, delivering consistent results for pressure vessels, tanks, and large-diameter cylinders. The process begins as the cylindrical workpiece is securely positioned on the rotating table. The BMB25's robust hydraulic system applies controlled forming pressure, while its precision tooling gradually bends the plate edge outward to the exact flange radius required. This cold forming method eliminates the need for welding additional rings, reducing fabrication time and ensuring a seamless, high-strength joint. Its programmable control system allows operators to set flange height, radius, and forming speed with remarkable accuracy. Real-time monitoring ensures the forming force is evenly distributed, preventing material deformation or cracking. The rotating table, combined with the synchronized movement of the forming roll, enables smooth, uniform flanges even on large diameters. The BMB25 is built for versatility, capable of working with carbon steel, stainless steel, and other alloys. Its heavy-duty frame minimizes vibration, while the advanced hydraulic drives deliver consistent torque for flawless forming. With its ergonomic controls and safety features, the machine ensures both productivity and operator protection. From shipbuilding to petrochemical plants, the Abbend BMB25 stands as a benchmark in flange forming technology, bringing together power, precision, and efficiency to meet the most demanding industrial standards.